This is just a sound check. I'm not hearing anybody. This is Dan.
Yeah, we got good comms. I think. I don't know. I got two different.
Yep, I heard you loud and clear. So I'm still learning Teams. So I'll go back.
Yeah, I think the meeting might actually be starting at 9:30. I think Will's email said 9:10, but the meeting invite said 9:30.
Ah, excellent. Well, knowing that, I'm going to step away for a moment and finish making some coffee. Thank you.
Yep, no worries.
Damn, 9:30. How's Hawthorne, Chris, or whatever you might be?
Sorry, what'd you say? I was walking away.
No, you're good. I was just saying, how's Hawthorne or wherever you may be?
It's not too bad. I've actually gotten to spend some time in LA instead of like spending all my time in Boca, which is great. Because for November and December, I think I spent like 2 weeks in LA and the rest of it down in Boca.
Wow. Yep, sounds about right. Hey, I'm gonna be in Hawthorne on next Friday. I'm interviewing for Star Shield. You know anything about Star Shield?
That's sick. I don't know. I know a little bit about it. It's like not as information available as like Starlink.
I figured.
I also don't know that much about Starlink because I don't care as much about satellites. Yeah, what do you want to know about it?
No, I was just wondering if you just knew generally.
Yeah, I think it's like we are more information available now. Like you should be able to Google a decent amount of stuff about it. I just don't think that like obviously everything is going to be there.
No, for sure. Cool. But like generally good things from anyone, if you know anyone on it, or it's not, I don't know. Just seeing if you know anything. It's fine.
If I don't take a massive bite of my sandwich, why do
Hello. Can everybody hear all right?
Yeah.
Awesome. All right. Still got about 10 minutes here till we're gonna get officially started, so just hang out. Get everything up on the screen here. How do I get it to show here and on the big screen?
Is there like a thing for screen mirroring options somewhere?
I've never done it with the like present in Teams.
Oh. You could download it and where's oh geez, I don't know the Mac commands anymore. Apple menu. Click the Apple menu. That one. Setting. System setting. Displays.
Oh, just to mirror it.
Yeah. There. And then displays.
Yeah.
Somewhere. It's got a little blue icon. Yep. And then use as. Click the name of your display on the right.
And uses main display?
Mirror
Mirror
built-in display. There you go.
Okay. Well, and then it's going to present it here though like this. Is that?
What's private view button do? Oh no. Hello.
Oh.
No.
Yeah. No.
It's like so close.
I go layout. Content only.
Can't think of. It's gonna put you in the corner. You can try to do it as an extended if you go back to the settings. Use as. Stop mirroring maybe.
Okay.
Stop mirroring and then click it. And then
Extended.
Oh, you know what you might have to do? You might have to. Where's the main? How do you find the main presentation?
This is. Oh, I see.
It splits into two.
Yeah.
It always.
And then I can still control it from here.
I don't know if. Yeah. Or wait, go back to the one with that it's on.
Here.
Yeah, and then is there? Click on the Teams. Like hold down left click. No, there should. Booster PDR. Click that. Usually it splits it into like two windows. Click layout. Oh wait, we already looked at that.
Well, I mean, it's fine to have everybody up on the screen. I don't think it matters.
Oh right, because it's from screen sharing.
Yeah.
Yeah, it's gonna show unless we do.
Mm-hmm.
Can we make this part bigger?
Oh.
Hide presenter view.
Aha.
No, that's too far. There we go.
Yeah.
So we could just mirror
Yeah, I
it.
like that.
It's probably good.
No, I think it was better the other way. Yeah. Okay.
Nice. Hide presenter view. Cool.
All right, and then I'll mirror it again.
Yeah.
That works.
Cool.
Thank you.
Tech support.
Okay. Yeah. Is there a clicker in this room that I could use to?
I don't know about this room. There might be one in 322. I can try.
Okay. Well, I can also. I have a. No, I don't have my.
You have a USB?
Yeah.
If need be, I have a mouse.
Oh, just gonna.
This is the comm check. I can hear you guys. I see your screen. If you don't want to see my mug up on that screen there, you could just extend your monitor, have the Teams app on your laptop, and PowerPoint up on the projector.
Yeah, there's no clicker over there.
Okay, no worries. Okay. Looks good to me.
But let me check, because I was trying not to change the nose cone. I can check that.
Yeah, because
And then if it doesn't work,
I like diverges. So like RPA. I was really good. Review is changed. But so I just found like the change in any will understand. And then I have to go this program. So
Oops.
The old people who pass out on the slots and they're still playing somehow.
Can't sit with your hands. Can you stand with your hands?
I don't think it's, now that we have this.
Using my phone during class. I don't want to do that. So I got either I can do a big key or this.
What is it?
It's called
What do you mean?
Yeah, so it makes a noise. I won't be doing that.
Did you see things that's just like
This one, oh,
use a normal pen?
but that's a little.
All right. I think we should probably get started now. About 9:30. Hi, everybody. I'm Cameron McClure-Coleman. I'm the project manager for the Sonata I, doing the recoverable booster program, starting it up with the vertical launch rocket plane that we've designed or are designing. So going to start here, just quick agenda. Going to do some introduction, talk about kind of the background for the mission, how we're planning on running our first launch, and then go into a quick overview of the different subsystems and what we've been working on those. Yeah, so get started here. So section 1, just going to kind of introduce some of the background. CPSS has a history with doing flyback boosters with the Starbooster project years ago. The Opus program that we're doing, we're hoping to bring back the capability of doing the flyback boosters and having central stage launched by 2 strap-on boosters like that. So this year, we've created kind of the first step in bringing that back with the vertical launch space plane that we're calling Sonata I. And it's going to be, the main goal is to have it be like a test platform for all of the components or like electronics configurations that we want to try out before building big ones that are more expensive and are going to take more planning and paperwork and stuff to get off the ground. So because it's primarily a test platform, we have been designing with modularity, manufacturability, ability to quickly kind of relaunch and iterate. And those are kind of our main focuses. And our long-term goal is to develop a platform that we could use flyback solid rocket boosters to get central stages up for projects like propulsive landers or space shots or what have you that would be multi-stage projects for CPSS in the future. So yeah, that's kind of the background. So a little bit more in detail on our rationale for why we're doing it this way. We've decided that we wanted to design to the constraints of having it be a small unmanned aircraft system, as well as the constraints of it being a Class 1 amateur rocket. This reduces the amount of headache that we have to do of being reliant on organizations that run launch sites or other kind of competitions and stuff that we do with our other rockets. And we can kind of, as an organization ourselves, independently manage and schedule ourselves a little bit more with the launches. Being a Class 1 amateur rocket, we do still have to, or we still would like to go through the proper channels and get waivers and stuff sent into the FAA and all that, and have all the paperwork done that you need to do the small unmanned aircraft system, because we'd like to practice that, and also because safety and all that is important. But we'd like to be able to practice working with that kind of stuff for future when we do bigger launches. We'll definitely need to have those skills and know how to do that kind of stuff. I'll discuss the constraints a little further in the mission requirements subsection. But yeah, that's just kind of the overview of our rationale for how we're designing it. All right. This is the second section on the mission requirements. Here's some of the constraints for Class 1 amateur rocket, mostly constraints like size and the amount of propellant we can use and how we can build it. Nothing crazy. You've all probably seen this before. And then also for small unmanned aircraft system, this is kind of what the FAA says about drones and flying drones. It has to be smaller than 55 pounds, which we'll definitely be able to do because we're keeping it under 3.3 for it being a rocket. And then just some mostly weather and stuff as well down here, making sure that you're in good conditions to be able to see the rocket or see the drone and all that while you're flying it. Yeah, so mostly not too crazy stuff. We're also taking into consideration, these are some other constraints that we've been building with in mind. There's some severe airspace constraints that we have to deal with launching in the actual San Luis Obispo area due to the airport. And then also want to make sure that we're not launching somewhere where we could start a fire in a field where there's a lot of brush or whatever. And then also making sure that we can launch somewhere where we can be sure that there's nobody who could be in the way or in the range of operations, and making sure that when we're building our launch operations and stuff that we have spaces for everybody who needs to be there to be safe and behind cover. Yeah, and then also in the human safety constraints, we have been developing a abort subsystem to deploy a parachute in case we lose control of the vehicle and all that. Our main goal is to recover it under wing power, but if that is not possible, we want to make sure that there's a predictable descent still happens, that we can keep it out of humans and their things. All right, and then mission objectives that we have written up here are main success criteria. We want to be able to get up to an apogee over 250 feet and under 400, because that's what we're capped at for a drone unmanned aircraft system. And we want to be able to have a relatively straight up ascent, and then we want to land after a successful glide phase. And for the first flight, we don't want to deploy the FAS. We're going to do other flights where we can test it and that kind of thing. And then secondary objectives, obviously, to gather data necessary to tune all the flight software parameters, and we want to be able to rapidly test different designs for airfoils or whatnot. And so gathering data on the performance of our physical components from the telemetry is important. And then moving on to vehicle overview. So this is just kind of our like mock-up diagram here, and then we'll go into further component detail later. But we're planning on building with large wings in the back, and then 2 canards with pitch control flaps. This is very similar to how Starbooster was built. And we figured we just kind of start with something that we know works, and then make it modular and rapidly relaunchable so we can iterate and test and tweak how we like it. This is kind of how we're organizing the payload systems with the motor in the back, and then the flight abort system that will deploy parachute down. We can talk about this further in the section on the flight abort system, but we decided to go this way because we figured it'd be pretty hard to fit it in a way that could come out the back, which would probably be the easiest for the parachute deployment. But for manufacturability, we figured a spring-loaded system kind of deploying downward would be the easiest to do, and also the safest, because we're not sure how the motor will affect a parachute system while it's burning out and getting hot and all that. Okay, and then just some quick overviews of the different modes of operation. While we're in ascent mode, we want to have the flight software configured to maintain a stable trajectory for us. And then after burnout, the vehicle will transition into the glide phase, where we will then have the remote operator take control of the control surfaces. The flight abort system, we don't want that to trigger while we're under motor power, so that will be switched into like an off state on ascent. And then all other electronic systems will have functioning normally, all the telemetry, data logging, video feed, etc. And then in the second mode of operation, after we transition, control will be handed over to remote operator. And then flight software will assist with stability corrections and stuff when needed. And then we'll have the FAS on standby, ready to go if we lose control or if we decide to manually abort. And then all other electronic systems functioning as they were. All right, and then gonna run through a concept of operations diagram here. So in the first stage, we're just on pad idle, confirm all of the radio control uplink and downlink for telemetry, and then confirm that we have all the authority on our control surfaces that we want. Confirm we have power to FAS, confirm range clear operations personnel at safe location, and then go for launch. And then we can do launch and ascent phase. Flight software, full control and authority over control surfaces. We maintain upward trajectory until motor burnout. And then at that point, we go into the transition phase. So we'll now be under remote operator control. Flight software provides stability support, and then we perform the peel and roll maneuver, peeling back, rolling over, and enter the glide phase. During the glide phase, main goal is to just keep it in a controlled glide, somewhat slow, not like super fast, gonna go ballistic. Flight software is now providing stability support as before, and then we want to navigate safely to the landing zone that we have determined. And then here, if the FAS deploys, we'll have a parachute, and it will slow the descent and make sure that it's on a predictable descent and not just kind of gliding out of our control into a tree or into a person. And then if the FAS deploys, we want the control surfaces to stop operating, so there's no chance that like they get damaged or they damage the parachute. And then if the telemetry and video transmission are operational, we'll continue just so that we have data from the GPS as to where the vehicle is, so we can go find it if it's too far. And then landing, power down, recover. Yay.
All right, I think
Moving
we have some questions. It's Chris and then Miles.
Yes, let's do questions.
Here with me.
Yeah.
Yeah. Okay, so couple things. First, I guess, what Mach number do you guys expect to be at the end of boost phase or ascent phase?
What Mach number?
Yeah, like how fast are you going to be going?
Like 0.1 Mach, I think at max. I think if I can pull up the Open Rocket, I think it's in the slides later, it was no more than 100 feet per second, and motor burnout like a second or two into flight 2 seconds.
Copy. And then, yeah, your flight abort isn't really an abort so much as it's just like deploy the parachute, right? Like you would not
Yeah,
stop
yeah. I mean,
your ascent. Okay. Copy. Have you guys looked into ITAR requirements for active control? This looks pretty missily if I look at slide 12. I just want to make sure that you guys are appropriately accounting for that.
Yeah, I mean, we've been reading through like what the requirements are for fixed wing drones and stuff from the FAA. We read through that whole document. I think it is linked here. But ITAR is a good one to look at too. I don't think we looked through that document on what classifies as a missile. We've just been going with what the FAA says is like what you should do if you are flying a fixed wing drone. And are trying to design to those constraints. But yeah, ITAR is a good one to look into. We'll put that in our notes.
Yeah, I do not think that that will like fully cover you for fixed wing drones. Like you are not under like power from a propeller or anything. This seems.
Oh, you think because it's under a rocket motor that? Sure.
Yeah,
Okay.
I think that might complicate things quite a bit.
Sure. I also wanted to reach out to they have a place on the website to reach out about like questions about waivers and what forms we should sign. So I wanted to reach out to whoever the coordinator was for the local like air traffic person from the FAA and make sure that we're doing it through the right channels. So that's somebody we can probably ask whether or not this classifies as like unmanned aircraft system or missile.
Yeah, and then I guess if you are going to talk about this later, you can tell me to like just hold my horses. For the flight abort system, do you guys use a drogue chute? And have you guys considered using like a mortar style where you have like a propulsive blast that shoots out the parachute instead of a spring-loaded mechanism?
Yeah, so we thought about doing the like propulsive blasts, but I mean we'll talk about this later too. But we thought that in order to be more easily kind of repackable, so we could do like a launch or 2 a day, or like go out to a field for a day and do like maybe 3 launches, that it would be easier to kind of repack it into a spring-loaded mechanism than have to do all the stuff for putting propulsive powder and stuff into our system in between launches. That was our main goal for that. But then we're not doing a drogue chute because it's pretty small, like it's under 3 pounds. And we figured we're not gonna be high enough for like drift to really matter in terms of like we want to have it descend faster and then deploy the main chute. But I think for a bigger version of this, it would definitely make more sense to do a drogue in our mind.
Yeah, and then for your abort, you said that's manual, or is that automated based on certain flight conditions?
So either. We have an abort trigger on the remote I'll talk about a little bit more with the flight software, how it works, but there's also parameters within the flight software kind of suite we've selected to use that you can set and tune to be like, they have options for, it's built for quads and for fixed wing. So you can kind of set, I'm a fixed wing, I want to do like the trigger my abort servo or whatever that launches my parachute when these conditions are met or when these conditions are met or when power's cut, defaults to throwing parachute.
Gotcha. And then why are you guys choosing to like deny power to the electrical systems in the case of an abort?
Just to the control surfaces, because I figured if we're under a parachute, having them kind of flap around and go crazy as a result of like the stability control, maybe we can just cut off that. But if it's under a parachute, I'd rather like eliminate those variables where either the control surfaces or the parachute could get damaged, because control surfaces are going to be like foam with tape over them, and having them knock against a parachute cord under tension might damage them.
What if your parachute deploy fails? Then you just limp mode the rest of the flight?
Sure, that's a fair concern. I guess we were thinking about mostly the reason that we would be deploying parachute would be that it automatically deployed because we have no power. But yeah, in the case that we still have power and the parachute gets cut, returning power to the control systems is probably essential. You can add that to the notes. Anybody else have questions before we move on to subsystems?
Yeah, I was wondering what your schedule looks like in terms of not only this project, but scaling up in the future.
Sure. Yeah, so we are looking to, in spring quarter, do first launch and hopefully kind of mid-spring quarter, so we have the option to do another launch day if we want. And we're still in the process of like selecting the best place, because that there's a lot of variables there. And so once we select where we want to, I think we'll have a better idea of when we can and what the best like target date looks like. Also, I think weather dependent as always with rocket launches and stuff. But yeah, we'll have more info on that for CDR and hopefully have a specific schedule. In terms of scaling up next year, we'd like to try launching a strap-on configuration with kind of a dummy central stage. And that'll be our goal for the end of next year. And then beyond that, scaling to whatever we need to for any sort of projects that'll have to be with communication with other projects and where they are, other payloads that are going to be developed, because I don't know if there's like a specific one in mind for what we need to constrain to yet for developing a bigger version of Sonata 1. But that's like 3 years from now is the goal, I guess. So I'm not going to be here when that happens. All right. Any other questions?
I've got a quick one. You said you don't know where you're launching yet? We
don't know where yet.
Okay.
Huh?
On campus or?
No,
like,
I don't.
Okay, definitely not.
On campus would be harder to probably. I don't know if President Armstrong, our best friend, would let us do that.
Yeah, no, for sure. If you're going like outside, even if you're going outside of campus, make sure that you get a permit from the fire marshal. I think is pretty important for launching these things.
Okay,
cool.
Yeah, for sure.
I had one quick question. This is Dan Macy. Is there a pilot in the loop at all, or is this fully autonomous, start to finish?
So there's a pilot when it's in the glide phase, and then we're hoping that we can kind of just set the parameters for the stability assist on the way up to just kind of keep it straight up, because human error when it's going that fast, we feel like would just kind of like to keep that out of the equation.
So in the case that like we're out of range to be communicated with the remote controller and avionics fail, how is the recovery system integrated?
Yeah, so I can talk about this further in the flight firmware section, but there's parameters you can set for like loss of radio link. So you can say like loss of control link delay, you can set to 3 seconds, 4 seconds, whatever we decide is appropriate. And then if it loses control for that amount of time, it'll do control whatever servos or output pins you decide on the control board. And we'll just have that, have our servo to release the spring, which will pop the trapdoor and whatnot off with the parachute. You can also have that for power, like loss to the board. You still obviously have to have power from the battery. So there's also parameters you can set for like a certain amount of like voltage if you're low on voltage to pop the parachute before you fully run out of battery. There's a bunch of different like contingencies that you can set and have in place.
I'll just add quick, anybody who's not near the laptop are hard to hear, so maybe as the presenter there, if you could just repeat the questions in the room, that'll help us.
Of course.
Thanks.
Yeah, so that last question was, how do you plan to trigger the parachute if you lose control from the ground? And so I was just going over how the flight software kind of controls that automatically. Any other questions on the front half before we go to subsystems? All right, we're good. Here's a quick agenda. We're going to go with lift and control services first. I'll let Kyler take over for that.
Okay, hello, I'm Kyler. I did all the lift and control stuff. You just click next or?
Yeah, you can do the arrow or space.
Okay. So this is a picture of the old Starbooster, or one of them at least. Pretty sure this is up in the hangar. If you've seen it in the room, it's in pieces right now. So to start out, I basically went up to it and took measurements, looked at the configuration and all that to try to see how the wings were set up. And then I also, this is a final report that was written at the end of the project. So I don't know a lot about this because there's not that much documentation. But basically, from what I could assume, I estimated the coefficient of lift to be between 0.15 and 0.3. This is just using estimated speed, because there's a video of it landing. And then the final report has a weight for it, and then the rest can just be done using the lift equation. And then, so we basically decided to keep with a similar design as the old booster, using the delta, or the same sort of delta wing with canard design. I guess Cameron already talked about this. And then, so basically we decided to asymmetric airfoils, because that'd be the easiest for launch, so that there's no tendency for it to, pull away when going straight up. And then to start off, I basically went through the NACA airfoil database to pick out several airfoils that are we could possibly use. This is one of them, 0006. Most of the SolidWorks stuff I've done so far has just been using this airfoil because it's pretty thin, so it would have a lot less drag, and then it also has decent lift characteristics, which is on another slide. Yeah, so on, I don't know if any of you guys have ever looked on the NACA website, but for every airfoil, it has a bunch of X-foil data for like coefficient of lift versus angle of attack, that kind of stuff. So basically, when I was picking out different airfoils, I was looking at these to choose what would probably be best. These are some options. I don't know if you can see what I'm pointing at on this. Yeah, sort of. These are all symmetric airfoils, just slightly different characteristics. Some have higher coefficient of lift for different angles of attack and such. And since we're making the design pretty modular, we can hopefully we can manufacture different wings and then clip them on for testing. And then for coefficient of lift, I was going for trying to keep it similar to the old Starbooster. And given our estimated weights, and we're trying to go for a glide speed of 9 meters per second, which is about 20 miles an hour, so around then. And so I use these values to help estimate the wing size.
Hey, sorry, quick question on the
Yep.
previous slide. You mentioned that you're going to be sweeping a bunch of different variables in that first sentence there by interchanging the wings. Can you talk about which variables you're going to be sweeping and how you think that they'll affect flight performance?
Yeah, so let me look on the other side. So for example, so this SolidWorks drawing on the right, or CAD mockup, is basically the old Starbooster. So for one, we could try using the same sort of delta wing ratios for route length to wingspan, and then the one on the left is just has the same surface area, so sort of similar lift characteristics, but just a different aspect ratio. So it might glide better. But then, what was I talking about? Yeah, so we're not exactly sure which airfoil will be the best. So basically just trying, going for the same lift by keeping the surface area pretty constant, but then trying different airfoils.
Yeah, I guess you're saying you're not sure which one will be the best. What metric are you using to determine what you mean by best? Do you guys have a specific glide ratio in mind, or a specific glide distance that you guys are aiming for, or is this just doesn't crash into the ground instantly?
I mean, the not crashing would be definitely be a plus.
You have the glide ratio up there that you're targeting, right? For the lift coefficient. Yeah, well, so we're just trying to target the coefficient of lift up on the slides, and then
get that glide and get a glide speed of 9 meters per second. I guess I don't have a glide ratio on here.
We had talked about one. I don't remember what we said. We had it written down somewhere.
Yeah, well,
Didn't make it on the slide.
Okay, didn't make it on the slide. I have it somewhere, but basically, since we're just testing it, as we try different wings, just basically see what's best for the pilot to control without not being able to land it, basically.
One of the other things we had talked about was the different roll control and stuff being affected by how we're placing our control surfaces on the wing, and so different wing spans and stuff will
I have that on one of these.
affect that as well.
Yeah, I have it down there. So we're also going to test different control surface areas and like how far out on the wing to place them, because most here, let me get on the right slide. Yeah, so we were originally going to go with like an Elevon design for just having the rear control surfaces just be Elevons, so for pitch and roll. But then since ArduPilot can test a bunch different, or can control for a bunch of different control configurations, we're going to test having these be Elevons or having them just be ailerons and then having the canards control pitch. So yeah, we're basically trying to test for everything.
Yeah, I think just having like a test matrix that shows which variables you guys plan on going through would be super helpful. Also, like in just determining how much scope, like right now you guys are saying we're going to go change the wing. And if you have a project manager that hears that, I think the big question would be how many times you're going to do that. And it makes it really hard to set like timeline based on that because the scope is very non-deterministic. So having like, we want to test 6 configurations, here's what we get out of these tests, I think would be pretty helpful.
The other thing to consider too is that you have to build all of these, and you're going to want to probably bring them all out on the same test day whenever you set that up. You're going to have those all prepped and ready to go. That takes more time.
Right, yeah, and then most of this should all be, I mean, the whole rocket body and all should just be one rocket that we're making, and then the wings will be the only thing that we're switching in and out. So since we're gonna, do we have a slide on the manufacturing of the wings?
Yeah, there's a.
Yeah, okay.
Yeah,
so the wings, I don't know what slide it's on, but the wings we're just gonna basically CNC cut out of foam. So hopefully that won't be too difficult to make a bunch of them. But yeah, that's definitely something to keep in mind.
Are you guys going to be reinforcing those wings, or have you checked to make sure they're not going to snap off when you launch? Speaking from experience with foam glider wings.
They shouldn't, given how small and the rocket is and how what am I saying? So how small the motor is, it shouldn't snap off. But yeah, we're thinking about that. We might reinforce them with, we're trying to keep the weight down. So like metal inserts or like basically just rods on the inside.
Or if you guys have access to any kind of layup, you could just do like a single fiberglass layer along the leading or trailing edge. It might just stop snapping.
Sorry, yes, and then we were gonna we might try that, but given how small this test platform is, it might be kind of difficult to get the carbon fiber to conform to the airfoil super well. But we were just going to cover it in sort of RC tape that a lot of RC planes use.
Sorry, I think I had like a poor understanding of the like magnitude of size. How big is like the root length and then your wingspan?
Oh, sorry. So the wingspan of, so like they're pretty similar, but the one on the right, at least I have catted up. If I remember right, I think it is 15 inches. And then
body tube is 3 inches in
diameter. The body tube is 3 inches in diameter. I'm pretty sure the wingspan is about 15 inches.
So 3.5 feet long.
Yeah, 3.5 feet long.
Yeah.
So so it's pretty small.
Could you have someone that's in the crowd tell us the CAD image up next to actual photo you have of people next to the old one from 2001 for a scale between the two?
Oh, yeah. Are you able to do that?
I don't know how we would do that.
Just whenever you guys have access to that, if you could toss it just into a slide so we could see it, I think that would help people calling in quite a bit.
Okay. Yeah, we'll do that. Okay, Cameron will do that in a second. Okay. And then so for the canards, looking at the old booster, the canards were angled up pretty significantly. So I don't know how to say it, like basically pitched up. So as the booster is going to be going up, then it would automatically be providing lift, which is great because the canards would stall first when you're flying it. But to simplify it, we're not doing that because we'd have to account for that for when it's burning up, and then it would pitch over. We don't want that. So our canard's just going to be straight on. What else? The current design, they're just the same airfoil as being used for the wings. Then the Starbooster had each canard size down to about 15% of the size of the wings. And so we're doing something pretty similar. And then so we're also going to test having, one of these images has it. Or not. Okay, it's on here somewhere. I'm sorry. But we are going to test having ailerons, or sorry, not ailerons, elevators on the canards for pitch control, which I mentioned earlier. And then the vertical stabilizer, again, is still just the same airfoil as used on the wings. The vertical stabilizer on the old Starbooster was pretty big. It's like 43% of the size of each wing. And we are going to use it with rudder control, but that's not a big concern, and especially compared to how much it might affect the drag and lift, or the drag and the weight, especially for launch. So we size it down to about 20% of the wing. Yeah, and then but we can of course change that out too if we decide that the yaw control is too poor. But again, that's not a huge concern. Yeah, and then Spencer, we're going to this later with the structures slides, but then this is basically just how we're attaching it. So each wing will have we're planning on making it out of acrylic, an acrylic airfoil cutout with these little slots on it that are basically just gonna, this will be glued, this cutout will be glued to the end of the wing, and then it'll slot on to the rocket body and just be screwed in so that we can switch them out pretty easily. And then I've already mentioned this, but the ailerons in the old Starbooster are about 12% of the size of the wing. And then since we're making it pretty modular, we can test this and change them out. But for the start, I think we're just going to use the same ratios. And then we're going to control it with one of these low profile servos, since we were going to put the servo in line with the control surfaces to make it just simpler, but we decided that it would be better to have them placed up in the body and controlled down with a rod like most RZ planes do. So that way we can switch out the wings a lot easier. And then we also are going to test, Autopilot has a built-in active control system, so during launch it can help stabilize itself, and we're also going to test that. We might not use that the whole time, but that is the plan. Again, for picking the servo, we were using this servo torque equation, which for the scale that we were using, it turns out that it doesn't really matter because most of the servos are plenty strong enough to control the surfaces, given the speeds that we're going at and how small it is. But this is definitely something useful for when we scale up. And then for testing, the general goals are to determine the ideal airfoil and delta wing configuration for performance and optimal apogee. Again, testing control surface sizing and the system. So if we're going to use elevons only or elevators and ailerons, and then mixing it with the active control system. Also for testing, make sure that the FAS works properly. That's supposed to be system, sorry. to assess to make sure that works if we trigger it intentionally or if there's just a loss of control or power. And then we haven't gotten to this yet, but there is going to be a camera in the nose cone, and we're going to have the pilot control that with an FPV view. So we're going to test that and tune it to make sure it works properly. I think that, yeah, that's the end of the lift slides. Any questions? Thank you. Okay.
Any questions? On to the structures.
Yeah, that's a done.
All right, so my name's Spencer. I'll be doing structures and recovery systems. First off, just go over general dimensions of the rocket. We have a length of, for the main body tube, which is the main section, it's only gonna be one section of body tube, 61.1 centimeters, which is roughly 23 inches, something like that. With a 3-inch outer inner diameter and just over that for our outer diameter. We are going to be making it out of phenolic tubing, which is basically a cardboard tube that's resin impregnated. It'll hold up a lot better than just traditional cardboard tubing will. It should have a compression strength around 5 times that of normal tubing. It's also heat resistant and only minimally more expensive than a traditional cardboard tube that you would use on more smaller projects. Yeah, so we decided to use this because we have the motor inside the tube, and unlike a traditional rocket system where you might eject your motor, we are keeping it in. So the heat might become a factor that we're considering in the exhaust or in the back part of the rocket. So we just want to make sure that we're not burning up while we're gliding. Otherwise, we should have, with this configuration, apogee of around 94 meters and a velocity of 41 meters per second, or max velocity of 41 meters per second. So again, it's not going to fly very high, but the idea is to get the vertical takeoff quickly and then test most of the functions during the glide phase. Additionally, our total mass of just the body tube is 343 grams, and the mass of the entire rocket system with motors or with the propellant is 1,476 grams, or roughly 3 pounds. And we're trying to stay within that range for the regulations and just to keep it light and so we don't have to over manufacture anything.
You guys' wall diameters
so
don't line up? Or you're like your OD with ID?
What was that?
You go, yeah. So you have an ID of 3.002 inches, OD of 3.064, and a wall of 62 thou. But your wall would contribute to double that.
Yeah, it looks like the wall
right.
fits on the encounter one.
Oh, yeah.
That's yeah, just a bad math. I'm just using.
And then the weight.
Yeah.
Sorry, go ahead.
Yeah, no, I'm just using a tube that we found on the internet. So I just did the outer calculation, but the inner calculation is the correct one and the wall strength. So ignore the outer dimensions.
Okay, no worries. And then the weight, the 343 grams, that is for the body tube alone?
Yeah,
or
just the body tube alone.
Copy, thanks.
Yes.
What is connecting the sections? Is
Oh.
it bulkhead, and so what's that made up of?
No, they're just inserted. It's a full body tube, and so because we were taking off part of the tube to put the spring loader mechanism in, and the top part of the tube to put the avionics bay in, we would just insert those and move them in. Yeah, it's not a connecting tube.
Yeah, just for some clarification, we're asking about connecting the segments of the rocket. All the red lines there are just spacers in between the avionics and the abort system. They're not actual, like full-on bulkhead, but because we're the recovery system is shooting down out of the rocket, there will be a hole there, and all the stuff will be needed to load in through the front. So they're just there to space out those components between each other. And then the nose cone will be attached with a coupler, or however they do that. Yeah.
Control. And then you have a stability of like 0.891 cal. Can you talk about, I guess this might not be a structures thing, maybe it's like airfoil stuff, but can you guys talk about how you chose the stability and what effects you think it might have on your like pitch control?
Okay. Do you want to talk about it?
Yeah.
Sorry, stability.
So who's asking?
It's
The
Chris.
stability that you have there. He's asking stability that you have there. What was kind of the rationale for designing that stability?
For the So basically, the trying to keep everything as far back as possible to keep the CG in the rear because the motor is going to burn out, and the CG is going to move forward. And I know the old Starbooster had a water dumping system in the nose. We're not doing that because it's way too much weight and too complicated. But we're just trying to keep the CG as far rear as possible, basically.
Wait, so if you move your CG, you said as far aft as possible, or forward?
Yes. Yeah. Well, for initial, before the burn, we're trying to keep it as far to the back as possible, so that once the motor burns out, the CG doesn't move too far forward.
Yeah, so can you kind of talk through why you are doing that? Like if you go to the extremes and have your CG like super close to your center of pressure or have it super far away, how does that affect your stability? And well, how does that affect your like basic rocket stability? And then how does that affect your like control algorithm?
Right, so can you talk about the rocket part?
Huh?
So like CG on top of
Sure.
CG for rocket,
Yeah, so I think what he's getting at is we're worried about when the motor burns out, how that affects the CG. And so the stability kind of reflects that in that we're trying to make sure that once after motor burnout that we have more control. We also are not sure how much we trust Open Rocket's readings on stability because after motor burnout, we have the canards that are going to kind of affect our center of pressure versus center of gravity. And we're not sure, we would like to do more testing in like more like full-fledged like fluid simulation software and stuff in order to get more accurate readings on that. I would like to look into how Open Rocket calculates that, especially with the canards. And definitely for CDR, we're trying to have like a nice fluid simulation that can give us exact numbers on those. But yeah, and the main rationale sorry, go for it.
A very simplified way of asking my question is, did you guys set a requirement for stability prior to designing this?
No, so we didn't design specifically with stability as our like constraint. We're trying to make sure that like we were more focused on the center of gravity and center of pressure. And we're hoping that because it's like an odd, not symmetrical rocket on the way up, that we can use the active stability assist to make sure that it stays pointing up rather than just relying on stability and center of pressure to keep us upright.
Yeah, so I think Miles's and my concern is that if you don't set stability in the correct range, which I will definitely say that I do not know what the correct range is. Miles is saying sub 1, but if you have stability too high, you won't have enough pitch authority on your canards, and if you set it too low, you won't have enough pitch authority on your canards. Like if you are too low in stability, the rocket can just like pitch out and then your canards won't be able to help you. And if you have it too high, your canards will not actually be able to pitch it correctly because your airfoil will like keep it too stable. So I think this is probably something to go look into, is like how to properly stabilize pitch controlled vehicle.
Yeah. Thanks for the concern. Yeah, we definitely need to get the models and stuff that we trust for CDR and have that constrained.
All right, move on. Okay, so for our nose cone, we're looking at around 15.7 centimeters in length, again with a 3-inch diameter to connect to the body tube, and a 2.8-inch inner diameter, so a bit thicker. This is because we're going to be 3D printing the nose cone, and we want to make sure it holds up structurally. So what we're going to do is we're using an elliptical shape just for the ease of manufacturing, and because we don't, since we're only moving at max like 0.1 mod, that we don't foresee that the shape of the nose cone will be a major contributor in air resistance. So we're just keeping it simple as we can to make it so that we can manufacture it easily and relatively cheaply if we can do that on campus. But we are also, in order to be able to control and have the FPV, we are mounting a forward front camera into the nose cone that'll sit underneath the tip. So it'll be pointing somewhat down to account for when we're flying the slight pitch up while we're flying, so that you have a somewhat straight on view if you're looking through the camera during the glide phase. During the launch phase, it won't really be that big of a consideration because we won't really be able to control it, but we'd still like to see where it's going, so we want to have it active at all times. And we're going to run a wire from that camera back into the avionics bay to transmit the feed back down to the ground station, whoever's controlling the rocket. All right, so we're looking at placement of our systems. The avionics bay, we place.
Can you go back one?
Yeah.
Why did you guys? Yeah, I guess for PLA, how do you think that the surface roughness will affect things if you're 3D printing it?
So how do you think the surface roughness will affect things?
Again, we didn't really think it'll be a huge factor.
We're only going like 300 feet.
The goal isn't really to get the max height that we really can out of it. We're really just trying to get it up into the air so we can test the glide capabilities.
Yeah, are you guys going to do any like processing after to try and help with that?
I mean,
even if it's not a big thing, like just sanding it down after would probably be helpful.
Yeah, other than sanding it down, I don't think we're looking at anything specific. We could also, I mean, we're not set on using PLA or anything if a different material is better. It's mostly just kind of a rough, low-cost option to attach it. So our avionics bay will be located somewhat in the center there, with a length of 12.7 centimeters and a weight of 907 grams. So this will account for all of our telemetry data and sensors that will be transmitting back down to the ground during flight. Again, our camera will be up in the nose cone and a wire will run back to the avionics bay to transmit that feed. Located behind that is, behind a spacer, is our recovery system that we'll go into in a bit more later, what that looks like. And then at the back, we have our motor mount. We're using model 6006. Weight should be around 60 grams, and we'll have a length of about just short of 5 inches. Yes?
What is your motor class?
Cost?
Class.
Class. Oh, F.
So we'll have F class, and we'll go on to that. There's another slide on the motor. Next, any questions?
I think the model number's I think it's actually the SKU from Apogee. I don't know if that really, like the model number is really
Okay.
Yeah.
Whatever. I just
nitpicking.
Looking at the motor itself. So it should have, the one we chose, we found online, have a burn time of 2.1 seconds, impulse of 80 newton seconds, and will be 124 millimeters or 12.4 centimeters long, have a mass of 126 grams, of which 37.9 of that is propellant mass itself. As you can see on the right, we're going to have the motor slide into the motor mount at the back with 2 centering rings to keep it in the center of our rocket. We hope that we can just slide it in and it fits really nicely. It should, because the mount and the motor itself are from the same company, so it should fit. But we might have to play around with that a little bit to see some tolerance on the mount itself to fit the rocket. And then, as we mentioned earlier, we're planning on keeping the motor inside the vehicle during the whole duration of the flight. So there's no secondary charge that would release it or anything that will apply after burnout. Only consideration is now the lost mass from the propellant itself that we have to account for during our glide phase. Yes.
What's holding like the rings on and holding the motor mount into the body tube? Is there anything holding it, or is it just
the motor mount just? Yes, cool.
Yeah.
The rings are just gonna be, the motor mount's gonna be in there permanently. And
Yeah, the motor mount. Yeah, so the question was what's holding it in. So the motor mount will be just permanently glued in or attached, fastened into the tube itself. So we shouldn't have to adjust that at all once it's placed in. But we should definitely, make sure that the rocket fits before we finalize it in our design. And then, yeah, it should slide. As I said, the motor should slide all the way back perfectly and line up with the first bulkhead that we, slide in fully.
You guys have a delay of 7 seconds. Is there a reason that you're using an ejection charge if you have a spring-loaded parachute?
I believe that is the ignition delay, or maybe not.
Yeah, I think it's ignition.
I think it's ignition delay. There shouldn't be any secondary charge.
The actual data sheet so we can confirm.
Yeah. All right. Meantime, move on. So we'll go to control surface mounting. So we believe that we'll need upwards of 5 servos for all of the control surfaces. And due to the tight constraint of our diameter of only 3 inches, we foresee that it might become a problem that we can't actually fit the servos inside the tube itself. We believe we should, but in case we can't, we're also considering having them stick out of the tube as needed, and then connecting to the control surfaces from there. So in the future, as we kind of finalize our design and determine the strength of the servos fully for every configuration that we have, we'll finalize the design of where they're mounted and placed. But generally, we'll just have servo mounts on the main tube itself. That'll be pretty permanent. We're not planning on moving the servos. The only thing that would change if we had a different wing configuration would be the arm that is controlling the control surface itself. The servo would remain in place, but that's all stuff that we'll design for when we're making the wings. And we'll talk a little bit more about the mechanism itself. As we mentioned before, we're thinking of a small acrylic sheet that will glue on to the main wings. We'll have to make multiple of them depending on the wing. If we end up using slightly different airfoils or different length roots for the wings, but they should be pretty easy and simple to manufacture. Each of them will have these little cutouts with bolt-shaped holes so that we can fasten it to the side of the rocket. We are going to design it so that even if we change our wing shape, the fasteners are all exactly lined up in the place for every single configuration. So we wouldn't have to have multiple screws or any, holes into our main tube other than the 3 that we'd need for any of the wings. We also
something you guys might want to check on this is check the minimum material at that bullet hole to the other side. Or when I was still in CPSS at one point, we tried to control the rocket with canards, not realizing that we had like 20 thou, and they just snapped off during install. So it wouldn't hurt to make sure that you guys have a realistic amount of material there. Maybe beef it up if you need to.
Okay.
Yeah.
Make the.
Oh, okay.
Yeah. And then only other consideration was that the plate itself will need to conform to the body tube's dimensions. So that's why we're making it out of acrylic, because we believe if it becomes a problem, we'll be able to bend the acrylic or permanently deform it into the shape of the body tube so that we can fasten it easily and to the plane of the body tube itself. All right, and then get into the abort system. So we decided to include an abort system for safety reasons. We realized that the vehicle could travel a lot faster and out of control than we at first were intending. So we started to look into parachute systems that will deploy out the rear of the aircraft. The problem with this is that since our diameter is so narrow and the motor takes up like a third of that space, it would be really hard to mount a system that we could find online easily into the space above or below the motor. We did consider lowering the motor to the bottom of the tube and then putting the abort system above that, but decided against that because that would offset the center of pressure and balance. And we did not want to do all the calculations for that and just thought it would be too unstable and risky. So instead, what we've done is we are planning on making a spring-loaded system that will launch a parachute out the bottom of the rocket during flight. This will mainly be used for the glide stage if we cannot control it or we have loss of power, or we are just falling out of the air, which is a possibility. So in either cases, it should deploy and slow down the rocket enough to kind of meet safety standards. We're planning on having a toggleable switch that will activate the system from the flight controls, and a system that will automatically activate if we meet criteria for like losing control or we can no longer communicate with the rocket itself.
Hey, real quick, how much mass do you have allocated to this system? Because a spring that's stiff enough to get you enough compression for enough force in that like 3-inch diameter, I guess, linear travel you're going to have is going to be pretty thick and heavy. And also, if you need to have your shear pins retained, you need to make sure that your force is really finely tuned, especially during launch, which is pretty aggressive. So I guess I'm wondering how much mass do you have allocated to this so you can have some flexibility in your design?
We originally had an off-the-shelf like drone recovery deployment system that we were going to use, but it was too big in the casing that they had. So we had that spring-loaded. It was a spring-loaded system. So we just used I think it was 100 or was it 200 grams?
Just under 200, yeah.
Just under 200 grams, and we're just allocating that much. But you're right, we should confirm once we know exactly what kind of spring and configuration we're doing, how much weight that's actually going to add, and not just assume based on the off-the-shelf component.
Mm-hmm. And the whole system itself needs a bit more designing and fine-tuning. So right now we're still at the preliminary stages of a concept, really. We're still considering options of pre-built ones online and even some more. We believe the spring-loaded system is the best method, but if we come across something that we decide will work better, we're not opposed to switching it out or changing up the design there. So right now it's kind of fluid and up to changes as the rocket itself changes.
Yes. Okay, thank you.
Did you consider shock cord at all? Because that's going to contribute to your gas a lot.
Yeah, so again, we're kind of just basing it off of what we found, the one that we determined we can't use. That one was 1 inch longer than the one that we would, in theory, be using, but it was also made out of fairly high quality materials. So we are determining that parachute itself should be around the same, but the whole system might end up being a bit heavier or less, depending on what parts we can get and if we can actually find something pre-built that we can just buy as well, which is still a consideration. And here's just like a little look at what we're kind of thinking. In the top right there, you can see a section of the tube, and the spring would compress up into the top of the body tube, where it'd be held in place, and then a servo would release that mechanism. The spring would spring, and then the parachute would deploy out the bottom and break the shear pins away out the bottom of the rocket itself. And again, here's kind of why we decided to use springs instead of carbon dioxide pressurized systems. In the future, for our future designs, we're definitely looking at more like pressurized systems for the recovery system, because we'll have a lot more space to play with inside the rocket. But for our preliminary design and the prototype, we're really restrained by the amount of space out the back of the rocket. So we're kind of trying to improvise a somewhat usable system that'll work for the prototype, and then that will be able to change later down next year when we scale up the rocket itself. All right, and then manufacturing. So we haven't really started any manufacturing yet. We're still beginning to finalize our components and materials, which we'll begin ordering after PDR. But for our nose cone, the wings, the canard, vertical stabilizer, and the engine mount, all of that design will be going into, will be seen for the CDR, and hopefully after that we'll have a good system for manufacturing. We don't believe that any of these parts will be too difficult. The biggest constraint was the wings themselves, which we anticipate having to CNC out of foam. So we have to figure out how to do that. But otherwise, most of the parts could just be bought online and connected. A lot of stuff will be glued in, and any of our modular components will have to be made separately, and then we have to make sure that we can interchangeably connect them. And we hope that our final assembly will be at the start of the spring quarter, so that we can launch then and have time to relaunch with new components or change any variables that we wish later on in that quarter. And then testing, we mainly need to test the recovery system and the telemetry system before we do a full system test. So both of those, the recovery system and the telemetry, will need to be completely done before we can done and tested before we can actually launch the whole vehicle and test out the wing configurations themselves. And I believe that's it. Yeah. So, questions?
Sorry, can we go back a bit? Yeah, I think you're giving Miles an aneurysm with that first sentence there. Yeah. Do you guys have anybody in the club who has either, like, I guess blue tag? I don't know if they've changed it since then, but like any experience with CNC mills, and or specifically, I think you guys would end up using the ShopBot. And if not, how do you?
Yeah.
Okay.
Yeah, we have
those
shop
techs
techs in the
have
club.
experience with either of those?
Sorry, what was that?
Do the shop techs in the club have experience with either standard CNC mills or the ShopBot?
And
yes,
if not, do they have a plan to get trained?
I believe they have experience with both.
There's
Or
also
at
classes
least-
this quarter that
yeah.
I'm hoping to take to get trained myself. If I can get off the wait list.
Yeah, and then I also, never mind, I can wait, sorry.
No, you're good.
Yeah, I was just curious about the like catch mechanism for the parachute. I think you guys mentioned a shear pin. What is the function of the shear pin there? Like you would have to have an active system to like deploy the parachute, which I'm guessing is going to be some sort of catch. And in that case, you don't have load going through the shear pin prior to the catch mechanism deploying.
So I'll go back to. So
Doesn't have to be a pin, I guess.
yeah, I mean, it doesn't have to be a pin. We're kind of looking at some system that will break away so that we can have a full body tube during flight. But if need be, we can release the parachute through the tube, through a hole, when the system is activated. So we're not really set on how we're going to do that, which is kind of the first thought. But we'll definitely kind of consider more options as we're going down and looking at fully manufacturing it. Yes.
I would say.
Okay, cool, thanks. Okay, cool, thanks.
To do calculations to make sure they don't break in flight before they're supposed to break.
Yeah, that's one problem with the shear pins is that since we have a vertical takeoff, the forces are going to be a lot higher than we would be when it's actually deploying. So we need to account for a lot more force than we might necessarily normally would. Right.
Are you planning on just using like a Dremel or a box cutter to cut that thing out?
Yeah,
okay.
Yeah.
And the nose cone, how is that attached? Is that just squeezed in?
Squeeze in or some sort of coupler that will go over it. The 3D printing should give us a good range, and we can remake it if we need.
Yeah, that makes sense. And last, the foam, how much is that? Like how much? It seems like you need a lot of foam because you're testing a lot of different airflows and stuff. How much is that going to cost?
Yeah.
Probably. So yeah, because they're pretty thin wings, so we figured we could just get the sheets instead of like big boxes of foam, so it should be careful. But also, once we have our test matrix for like how many wings we want to test, we can be more specific on the total cost of that.
All right. Yeah.
I had a quick question about the mounting plates you're using for the wings. So you said you're going to do those out of acrylic. Do you know what type of acrylic? Like, are you talking like plexiglass or something more like bendable?
Something hopefully slightly flexible.
Yeah, I mean, if it won't flex up at the form of the body, we can just like keep bending.
I would only, so if you're using like a plexiglass type of material, my like only words of advice is if you do plan to use heat to heat them up, just be really aware that like you will have heat affected zones, like where your mount's attached to your, and acrylic is really brittle. So I would try and find material that's more bendable and try to avoid using acrylic because like the heat
Do you
affected
have
zones.
suggestions for a more heat moldable material?
Not at the moment, but I could look into it.
Thank you.
Fiberglass plate you can buy stock.
Okay.
Yeah.
So how are you going to see on the nose cone with the camera if you go back to that slide?
Yeah. Yeah, so yeah, this doesn't have it, but the camera itself will have a mount inside the nose cone. Since we can 3D print it, we can design it with that in mind. So somewhere around, I mean, if this were the bottom, but like a little cutout there, which it would stick out along the face, and then the actual camera itself would be positioned in towards the center of the nose cone. So.
Okay, and you said that's going to be at the bottom because you want it to pitch down?
It'll be at the bottom because when we're gliding, we anticipate that will be pitched up, so that it'll look straight out the front when it's flying.
Okay. Why do you anticipate you're going to pitch up? Because according to your open rocket, like the CG is in front, so.
Well, just because when we're flying, since it's such an airfoil, there's no like lift on our own, so we're going to have to be manually pitching up the whole time in order to glide. Is that what you're asking?
Yeah.
Okay.
So with that, do you know what your stall speed is?
Well, yeah.
We have our glide speed target, but the stall speed not less than exactly sure, less than that, yeah.
And we also anticipate, I mean, the whole system, the main constraint was just landing. So it's going to be a pretty quick descent. So we'll be using kind of that profile to land quickly, and especially right before landing, since we're going to be landing on basically skid plates on the bottom, or just the tube itself for this design. We're going to have to pitch it up as well to slow down that speed to get a smooth landing, if we can.
And when you do fly, you're just going to aim for that target speed that you said earlier?
Yeah, because that'll be all manually through the first person view camera. And, yeah.
Comment. Does that have a shoulder on it that it's blocked by the view, or is there? Because if you're going to shove it in, there should be a shoulder on it. Okay.
Yeah, it's just a nose cone. It's not
Then make
exactly
sure that's an
what it is.
open rocket as well, because that should add a little bit of weight.
Okay.
And how big
Okay.
the shoulder is.
Smart. Anyone else? Any questions? All right. Should be on to avionics.
Okay. The room next door is now clapping. Okay, moving on. I am now back for avionics radio control. Just going to do a quick rundown of the components we've selected and then go talk about software for a little bit too. This is the flight controller we decided to use, getting it from the SpeedyB, built for specifically fixed wing remote control application or radio control, because it's got a lot of nice pinouts and features that we can just add servos and other things that we need to control. It has enough for all of the, I think, 7 total that we want to control, and then has dedicated pinouts for the cameras and telemetry transmission and stuff that we need. And then also the same company manufactures a lot of those components that are built to work with the board, so we don't have to worry about compatibility as much because we already know that it's been tested with the board. It also has stuff for micro SD black box logging that is pre-set up, and then plenty of pinouts for airspeed sensor and GPS that are like dedicated pinouts for those. And then here's the wiring diagrams that are in the manual. Not all of this stuff is what we're going to use, but just kind of put it up here so I could give an idea of where different kinds of things go. So we're going to use I have an ELRS receiver selected, so we would use the ELRS pins here, and then all of these ports here are for where you would put servos, and then there's a dedicated airspeed sensor pinout that might be easier to see here. And they have an option there where you can just plug it straight in, or we might, depending on where we mount it, need to have our own kind of custom length pins that we'd want, or cords that we'd want to solder ourselves, so you can do that. And then all the video transmission and GPS stuff also have pinouts and options to solder them in as well, depending on where we place them. We might need to solder it on instead. Any questions on the electronics? And then radio control flight software stuff, planning on going with Ardu Pilot. It's pre-built, open source, has a lot of customizability, and we could customize it ourselves if needed, although I don't foresee that being a necessity anytime soon. There's full support for fully autonomous UAV missions, which is kind of cool. We might look into in future missions, but not planned now. Also, there is ways to integrate that with OpenMCT, which is something that other projects are interested in using, and the whole club is kind of interested in developing with as well. So just kind of like aligns with some of our long-term goals as well to get good at using this software. Any questions on those previous 2 slides before I move on? Sorry. Nope. All right. So this is a radio transmitter that I picked out. Obviously, there's many similar options, but this one was just the one that I picked out for cost, and it comes with the OpenTX protocol kind of already flashed to it. And so what that is going back here to the receiver thing here. So the receiver, if it has is transmitting telemetry down to your controller, this OpenTX firmware on it will be able to unpackage that and put it on the LCD here in like a little navigation heads-up display sort of idea. And I figured that would be helpful for if we do lose video, but we still have control over it, that telemetry will likely get down easier than video. And so I've seen that people like to have that included on RC applications for like fixed wing stuff so that they can still kind of control it and fly it back into range of video if you lose video. And also it just seems fun and like a fun project to set up. So yeah, this is more description of how plan on using the OpenTX software there. And then I have a quick little components list of just all the kind of stuff that I have selected. And then just a little note that there are people in the club who own goggles and controllers and stuff that we could borrow, or friends of ours that we could borrow if needed to cut costs, because I know that we're pretty constrained on costs for this project. We're definitely under budget still on this stuff, but depending on how much we want to buy in terms of foam and other things for the physical components, we might have to cut those costs and use an already existing radio controller or stuff like that. Yeah, and I think that's the last slide on the electronics and stuff. Actually, the last slide in general. So any other general questions?
Do you know what the budget looks like for the rest of the project? You mentioned that you're under budget. How's that looking with all the components that you've covered so far?
Yeah, so I think the total budget was 700 to 800, about 780, I think is what it was. So we've got another like 250 so to play with. I think that with the foam and the abort system, we might go over that. So that's why I'm saying here that we might have to cut some of these down or pick cheaper options, or use like ones that we own and just borrow them from club members for the mission.
Because it seems like with your testing plan right now, if you guys have to use a new motor every time, that could be pretty costly.
Sure, yeah, and that's part of why we're also going with smaller motor, is that instead of buying like a $200 motor every time, it's only like $20 to $50 price range, hopefully. But yeah.
And then along with that, the pilot, are they going to be equipped with like the velocity? Like, is that going to be sent down?
Yeah, so that's part of what the OpenTX is for, is that you have that display there. There's also software that you can do, depending on the goggles that you have. You can get it as a heads-up display in the goggles for airspeed and all of the like kind of telemetry, navigation numbers and stuff that you need.
And they're going to be able to see like the live video also?
Yeah, so you put goggles on the person, or you can have it go from the goggles to a screen, and that will have the live video with the telemetry display on top of it. Or if you have it on a screen, you can look at the navigation on this LCD if you're using that firmware on your controller.
Right, thanks.
Hey, I don't really know a whole lot about RC plane control, but how does a digital airspeed sensor work?
Yeah, so I can pull up the actual airspeed sensor that I have selected if you want to see, but it basically just has 4 pins. Where is it? 4 pins here that it has a power, ground, and then the two. Let me find the actual data sheet for it, and I can pull it up more. But the one that we selected has like a tube, and then like a pedo tube that you can just mount on a wing or wherever you want, and then that tube comes out to that digital board there that just kind of runs the sensor on whatever the pressure is in the tube. And so we would have to make sure that we design so that we're not like kinking our tube and affecting the air pressure.
Gotcha. So you're just going to mount that on the wing or the rocket body?
Yeah, on the wing or the nose cone or however we decide is the best spot for it.
And just make sure it's outside your boundary layer. I know you're going pretty slow, but
yeah,
you
sure.
don't want to be getting your static pressures.
Yeah.
I know you said you don't have much manufacturing plan, but CNC milling, or how thin are those wings?
Yeah, so that is a concern, the thinness of the wings with the CNC milling. We might like realize that it's too thin to CNC mill and then have to choose a thicker airfoil or scale it up somehow.
We were thinking about also just like, spars and then like some RC planes to print out the spars for sections and make it over them. That's just difficult to get because it's hard to keep the airflow constant.
Another manufacturing option we looked at, if we have to scrap the CNC milling idea because it's too thin, is you can print out a spar on either end or use like a plywood kind of guide and then use a hot metal foam cutter. And I've seen that that's pretty popular for RC plane foam cutting. We just figured that because it's not a flat like rectangular wing, that it would be harder to do that, and CNC milling would be easier for a delta configuration.
Right. CNC milling the first part should be fine. But since it's symmetrical, flipping it over, that's going to be hard to like hold it if it's only held on.
Depending on how thin it is, it might just snap. You're saying, it's definitely a concern. So, any other questions?
I know they were asking to see like a model. If you go to slide 25, I just put a scale comparison, sort of.
Slide 25. What update?
It's 50/50 and
no, it's not.
Okay. Well, did it also get posted in the channel?
We don't put it.
If you reply to the meeting.
This.
Yeah. It should show up in the chat.
Oh yeah, there's a picture in the.
Oh, there's now.
Oh, and now a mock-up. Yeah, much better picture.
In the chat.
All right. Anything else?
I got one more question on your servos. Have you done any analysis on the like relative torque authority of those against the torques you're expecting to see on your ailerons or elevons, whichever you go for?
Yeah, this is the slide on that. And so, yeah, I think Kyler ran through and with the equation.
I ended up doing the calculations for a couple different configurations, and it ended up just because of how small and the wing where the control surfaces are and how slow we're going, it doesn't really matter because most of the servos that you can buy online are already well above the required torque.
Yeah, so he's saying that the servos that we selected were well above any kind of torque calculations that he was able to run through the equations for on all of the control surfaces, and so he doesn't foresee it being an issue.
Okay, that's including your launch velocities, right?
Yeah, he included the launch velocities.
Okay, thanks.
That's your question. All right, one more.
So I noticed there's a decent amount of electronics and servos, but I didn't notice any mention of how you're going to power them, or how you know you're going to have enough power for all those systems.
Yeah, so I forgot to mention in here, I think it's a thing, but this specific flight controller comes with a power board underneath there. That's the power distribution board, and then you would use a small drone battery that they sell as well that are meant to fit that power board, and it's got all of the distribution pinouts that you would need to power if you had every single one of these pinouts on your control board. It has all that with it because it's built to function with it. And it comes with all the stack separator and spin-offs and stuff too, which is nice.
What are some next steps that you're hoping to take for CDR? What do you want that to look like?
Yeah, so hopefully CDR we have like full CAD model done of how we're gonna put everything together. We want to have our test matrix done, and then full scheduling of like selected launch location and dates. And once we have our test suite, it'll be easier to kind of have that specifically like, oh, do we need to have 2 days to fit in the 6 tests that we want to do, or are we only doing 3 tests and we could likely do that in 1 day?
And also because of how difficult manufacturing wings might be, that I'm going to test that.
Yeah, and then have a full testing schedule would be nice as well. And then, yeah, so hopefully mid spring quarter, we'll have that first launch. All right.
This is Dan online. I've been holding my comments because I just had a bunch. But number one, thanks for inviting me to the PDR here. This is spectacular. I'm hearing a CDR, I heard, so that's awesome. I hope you invite a number of these folks here to that, as well as if you have any sort of like flight readiness reviews, that would be awesome. I'd like to share also just some comments, not to drive designs or anything, but just to have you guys scratch your head, think down the road as you're moving into production. Number one, I love that you're going to do fast turnaround iteration times, and so all that manufacturing stuff, we didn't delve into the details. I would consider putting a lot of effort into whatever you can do quickly and rapidly. Quick and dirty is probably what you want to do in this case, because you're going for cheap. A lot of lessons learned for you guys, and then eventually you'll iterate up to a more complex and robust system. So I'm just going to hit a couple points, and I'm going to stop talking. You might want metal gears for your servos. We've stripped many servos in past rocket flights because of the vibrations on those control surfaces on launch. That high-speed transition, going up to 100 knots or more, and then going back to your 20 knot cruise speed, you can just vibrate those nylon gears. So consider that. It's going to have a little weight, a little cost. I think the way you're mounting your wings right now, that acrylic is going to be too brittle. I think somebody mentioned that. Lexan, polycarbonate is maybe another option, but structurally, you might want to go with what most aircraft have, which is a spar system, and maybe you can have a way where it slides on, locks into spars. Just consider thinking about that a little bit more. You get that bending moment right where it's going to meet the wing, and it's not an easy connection point. I'd consider going with simplicity and not having a rudder at first. I think you can always add a rudder later. You might find a straight vertical speed, a vertical only, be adequate for your stability on both for rocket and for airplane mode. Speaking of stability, I think we touched on it already, and Chris highlighted the importance. You're going in the wrong direction from a aft CG with the rocket motor full to burning all that fuel and moving it forward when rockets want a forward CG and airplane want an aft one. So I'm hoping you guys are paying close attention and thinking, kind of scratching your heads of ways to do that. I know you talked about the water system we used on the Starbooster project. I'm actually in that picture with the little orange rocket. I'm the pilot hiding behind the airplane. But it is definitely something you want to consider, because rockets are stable passively with forward CG, and aircraft want to be closer back towards that. Yeah, there I am, hidden in the back in the shadows there by Trevor Foster. I see Clint Bashir on. Hi, Clint. Sorry, my computer just went to sleep mode. Okay, I'm almost done. Sorry, guys. Appreciate it, and everybody in the room. The 3D printed nose cone, I'm really into 3D printing, and I think that you might want to reconsider that and how you use it. It may be better for prototyping and tooling. It's kind of heavy. PLA, any of the materials you can 3D print for the structure you need, your strength to weight ratio isn't super high on those. But something to consider is maybe another option there. Or maybe you make it really thin, like a vase mode, I don't know, and put structure inside that's also your airfoil sections. Consider beefing those up and making them a little thicker, or even going with a non-symmetric airfoil. This rocket you see in front of you was going pretty fast, and we defaulted to those symmetric airfoils, but boy, it also flies fast then on the way back down. And I think at the speeds you're talking and the weight you're talking, you could get away with potentially some thicker airfoils, or even non-symmetric. And then lastly, for that parachute deploy, I heard Chris and the person who's sitting with him bring up concerns there. I just want to throw out the idea, there's probably a lot of other ways to deploy a parachute that aren't explosive in nature, but also are simplistic. So maybe consider torsional type springs and hinge doors and throwing a parachute, or I don't know. But anyway, just kind of, that's a perfect thing where you can build a number of 3D printed apparatuses and give it a try and see what you can do. And last but not least, we flew our this big rocket. We had little models that were foam models, very much to what you're trying to do. We flew those in glider mode just off the peak of like Madonna mountain out there. We'd climb halfway up the mountain on a windy day and throw them into the wind, and you can get quite a bit of good piloting time and tune your system without having to launch this rocket. Okay, I'm gonna stop talking. Nice job, everybody.
Thank you. Thanks so much for all your great additions and questions and stuff. thanks all for coming. I think unless there's any other questions, we're going to wrap up here. Anything else from people in the room? Anybody online?
No, nice job, guys. Good
Awesome.
work.
Yeah, thanks everybody for coming. Thanks for all your comments. Great to hear from everybody. All right. Good to see you all. I think should we just end the meeting then?
Unless anyone wants to stick around.
Yeah, we're just hanging out. Yeah. Will says hi.
I say hi. Hello, everyone. Thank you for
pulling up.
I will.
That's news. How's the Southwest? How's that going? Oh,
it's pretty good. It's pretty good. It's pretty cold. Oh,
it's cold right now.
Dude, it's been like sub 40 every day. Mornings have been like 20s.
Yeah, of course. We also said the motor mount is going to add.
It's cold. It's sad.
Oh, also, do you guys think you could retroactively go and just put all of these recordings on YouTube so that they're a little easier to send around?
Hold on, I didn't hear you. I think I need to disconnect from the.
Hey, before you do that, go check the ITAR thing, please.
I think they have technically done it before.
Could you say that again?
But before you post this on YouTube, please check out the ITAR stuff.
That work? Okay. Just cut the off. They are. I just completely.